Okay, so if you want to know the degree of polymerization, which is basically how many monomers in one polymer. So wait, let's see. Let's see. Okay. Wait. Okay. I don't know. Like I want a good example. This is okay. So basically, this is a monomer. So this is a polymer because as I explained, a monomer is different than a monomer. A monomer is one unit of a certain element. It's only monomer because mono stand for one. Polymer is many repeating units of a monomer. So the polyethylene, it's basically many repeating units of the monomer. The monomer here is ethylene. So polyethylene is many repeating units of ethylene. So okay, the degree of polymerization is basically we want to know how many monomers in one polymer. Like as this is the monomer. Anyway, we don't have to really calculate it. It's not required. I yapped a lot. It's just an idea or a concept that we need to understand. Okay, we also need to understand this graph. This one represent the relationship between the frequency of the chain with the chain length. Okay, so let's say we have this length, this one is one length. If the higher frequency we get, the higher chain length we get. So it's a direct relationship. So if we have a chain length, a very big chain length with low frequency, it will be low. But the thing is, the more frequency we have, the more length we have, the less weight we get. And the average is here. So anything beyond this average, like it will decrease, the weight will decrease, and we will get a very thin or a very light polymers. Anyway, this is not as important as this one. We have two kind of polymers. Okay, we have a homopolymer and a copolymer. A homopolymer is basically the same. It's a polymer with one repeated unit of a monomer. Let's say this is a monomer and this is a monomer. This is a monomer and this is a polymer. It's the same repeated monomer. It's no different. It's the same. It's exactly the same. Copolymer is actually the quite opposite of a homopolymer. It's more than one repeated monomer. So we have this is a monomer, this is a different monomer, this is like this, and we have a categories for the copolymer. We have alternative copolymer, which is it's like this. It's repeated. It's one after the another. We have a block of polymers. So this is one monomer, this is a different monomer, and this is a different monomer of the same first one, and it will repeat itself. The others are irrelevant, we don't really need to know it. Okay, so how do we classify a polymer? How do we know if that's a thermoset, if that's a thermoplastic? How do we really determine that? We need first to understand the concepts, like the chemical structure of the polymer itself. Okay, so here we have the first structure. We have linear. As I explained this one before, which is the bond structure. This is a carbon, this carbon, like this. It's going like this. So when a heat, it's a thermoplastic. Why is it a thermoplastic? Because when heat is applied, this will extend to this part and this will extend to this part, and it will be so easy when heat is cold or it cools down. It will be so easy to get back into the same size. That's why it's a thermoplastic. It's not a thermoset. Okay. We also have the branched polymer. It's a thermoplastic. It's going like this. This is a linear, and within one carbon, we have a double length, double chain carbon unit, and it will go with another linear, and this one and this one. It is obvious from the shape. If you understood this one, which is this is it. This is one carbon, this is hydrogens, and this is carbon, hydrogen. We will have a bond with this hydrogen, a carbon, and we will get a branch. If we go back to the slides, we had the same thing. Yeah, this one. This is the octane. If you see, like, this is the linear octane, this is the branched octane. It's different properties, but the same exact compound. See, we have a polymer with a chained branched monomer. So this is the second type. It is a thermoplastic, but we have exceptions. If we have a lot of branches, it will be a thermoset. Why? Because the heat distribution, when we apply heat, it is like really hard for the polymer to get back to its shape, to the complication and the structure. Okay, so we have a star polymer and a polymer network. A star polymer is also depends. It is a thermoset and thermoplastic. It depends on the cross length. The more cross lengths we have, the more likely we will have a thermoset. The length does not like it. It doesn't give a big deal as long as the cross link and the numbers of the linking networks. The more cross linking networks we have, the more likely the polymer will be a thermoset. Polymer network. Actually, this is purely thermoset, because there is no way in hell, if we apply heat into this structure, it will back to its original shape. It's really hard. It's impossible actually. So it's a noodle-like structure, and that's it for the how do we determine if that's a polymer, if that polymer is thermoset or thermoplastic.